Good morning, students. Only three are joined.
Good morning, doctor.
Can we start? Okay, I think we'll start. Okay, so is my screen visible?
Yes, doctor.
Okay, so yesterday we have started with the inverse Z transform, and we have seen the different cases for that. Okay, so what we have done there, so basically, in to calculate the inverse Z transform, the h of z will be given and the region of convergence will be given, and accordingly we need to apply the standard formula for the inverse z transform like this. Okay, now so we know that there are some standard signals, and for that this is the z transform and this is the region of convergence for this. Okay, so we can compare the given example, the h of z in the given example with the standard this z transform. If it is applicable with some adjustment, then we can directly apply that formula. Otherwise, if it is in the form of polynomial like this, then there are three major cases. One where is the number of poles are greater than number of zeros and there are no multiple poles at the same location. That means the poles are not similar. The other case is where the number of zeros are greater than number of poles and all poles are at different location. And the third case is where there are multiple poles at the same location. And in that case, there may be the number of zeros are greater than zero poles, or number of poles may be greater than zeros, like that. Okay. Now, mostly we will do the partial fraction expansion only in the case where the numerator polynomial is having higher order than the denominator. In that case only we will do the this long division method. Okay. Uh, Otherwise, mostly we follow the this partial fraction expansion. Now, if when there are multiple poles at the same location, so in that case, we are having this formula to find out the constant C. Okay, this long formula. Now, today we will do some properties of Z transform and the some couple of examples on the inverse Z transform. Okay. So there are some property we have already seen like linearity, time shifting, and differentiation. We have already seen it in the Z transform lecture. Today we will do all this. Okay, the remaining properties. So linearity property, we know that Z transform is linear. So we know that Z transform is linear if A and B is multiplied with H1, H2. And this addition is nothing but A of H1Z plus B of H2Z. Okay. Now, the main concern is about the ROC, region of convergence. Okay, for H1Z and H2Z, maybe region of convergence is different. So, the region of overall region of convergence is the intersection of these two ROCs. Okay, that is ROCH1 intersection ROCH2. Now, in time shifting property, if we have shifted time in the n domain here, then in the z domain, this is z to the power minus nd h of z. Okay. Now that h of z, except this nd is greater than 0. If z equal to 0, this nd is greater than 0, and if z equal to infinity, this nd is less than 0. Now scaling in the Z domain. Scaling in the Z domain is, suppose h of z, we are scaling the z by a. So that is z by a. Now for this, the h of n signal will be like this is a to the power n h of n. Okay. So if we are having a to the power n h of n, then in that case, this is basically the scaling in the z domain. Okay, and this is the ROC is, we are doing scaling, therefore modulus of a into ROC of h will be the ROC for this scaled h of z. Time reversal. Time reversal means instead of h of n, if we reverse the time, that is h of minus n. In case of time reversal, the z transform will be h of z inverse. Okay, and the ROC will be inverse of whatever ROC we are having for h of z. ROC will also get inverse. Okay, differentiation, we know that if n is multiplied to h of n, then in z domain it is minus z d dz of h of z. Okay, ROC will be the same like h of z. Then the conjugate we represent with this star. So h star n is basically the conjugate of h of n. Okay, so for h of n we are having h of z. So for h conjugate of n we are having this, in the z domain it is h conjugate of z conjugate. Okay, and the ROC will be the same h of z. The convolution, we know that h1n convolved with the h2n. This is basically the multiplication in the z domain. And the ROC will be the intersection of these two ROCs. And we will be having initial value theorem and final value theorem here. Okay. So that theorem we will see at the end. Now let us take an example on the linearity. So linearity property, we know that this is the linearity property for the Z transform, and this is the ROC region for this. Okay, suppose we are having example like this. So here h of n is minus 1 by 2 to the power n u of n plus 2 into 1 by 3 to the power n u of n. Okay, so we know that for the Z transform for a to the power n u of n, that is 1 minus this A Z inverse, correct? So the Z transform for this is 1 by minus minus will be plus 1 by 2 Z inverse. For this 2 factor is there, therefore it is written in the numerator, and the Z transform for this is 1 by 1 minus 1 by 3 into Z inverse. Okay, now the region of ROC for this first transform is Z greater than 1 by 2. Correct. This is the right-sided signal. So therefore, this is modulus of Z is greater than 1 by 2. For the second signal, it is modulus of Z is greater than 1 by 3. Now the overall ROC for this h of n will be the intersection of ROC1 and ROC2. Okay, so ROC1 and ROC2 intersection means if we draw the ROC on the Z plane, so the first ROC is 1 by 3, and we are having this is 1 by 2. Okay, so we are having the Z transform greater than 1 by 2 and 1 by 3. Okay, and this is basically the greater than 1 by 3. So what is the intersection of this? The intersection will be this ROC, that is the outer extreme ROC. So the intersection of these two ROC will be modulus of z greater than 1 by 2. Okay. Now suppose we are having this type of signal h of n. So our h of n is 3 delta n minus 1 plus 2 1 by 2 to the power n u minus n minus 1. Okay, now you can see this is basically the left-sided signal. So you should know what will be the ROC for this. Okay. Now for delta of this delta function will exist only at n equal to 1. Therefore, the z transform of this, we know that this is z to the power minus 1. Okay. Now this we can write. Now we know that the z transform of minus a to the power n u of minus n minus 1. This we know. That is 1 by 1 minus a z to the power minus 1. Here, this is plus. So we can take this minus outside and we can write this minus of 1 by 2 to the power n. So this is minus 2 into minus of 1 by 2 to the power n u of minus n minus 1. Therefore, this minus sign is here and 2 factor is here. Okay, and this the z transform of this minus of this my 1 by 2 to the power n u of minus n minus 1 is 1 by 1 minus 1 by 2 z inverse. Okay, now for this delta function we know that the ROC is greater than 0. For delta function it is modulus of z greater than 0. Okay, now for this is the left sided signal. Therefore, this is having the interior ROC. Okay, so the modulus of z is less than 1 by 2. So if we plot this ROCs, so this is my z plane. So for the first ROC1 is the z is greater than 0 except 0, entire z plane is my ROC1. Okay. Now, what is the ROC2? So, ROC2 is the interior ROC with the circle 1 by 2. So, this is 1 by 2. This is ROC2. The radius is 1 by 2. But this is negative signal, left-sided signal. Therefore, we are having interior ROC. Therefore, if we do the intersection of these two ROCs, so what will be the final ROC we'll get? So we'll get the ROC in between 0 and 1 by 2. Okay. So this is very important. So if in the exam, this type of question, if will be there, then you need to also draw the Z plane, this ROC regions, everything. Okay. Mention x-axis, this is real of Z, this is J times imaginary of Z, like this. You need to mention everything with figure. Okay, the next property is time shifting property. So the time shifting property, we know that this, if it is shifted in this time, then this is z to the power minus d h of z. So time shifting property, if we take this example, now this is, we know that the delta function is shifted by minus 3. So therefore z to the power minus 3 is the h of z. Now here we are having 2 to the power n by n minus 2 u of n minus 2. Okay, so if this signal is shifted by this 2, then the Z transform is, this is a to the power n minus 2 u of n minus 2, then the Z transform is Z to the power minus 2 and the h of Z, that is the Z transform for this. Okay, so this is basically a to the power n minus nd u of n minus nd. So the Z transform for this Z to the power minus nd into h of Z. And what is h of Z? Z to the power minus nd into 1 divided by 1 minus a Z inverse. So this formula is applied for this. Okay, therefore it is z to the power minus 2, 1 minus 2 Z inverse. Okay, and this is again the right sided signal, therefore modulus of Z is greater than 2. And what will be the ROC for this? For this delta function, ROC is modulus of Z greater than 0. And for this function, the ROC2 is modulus of Z is greater than 2. So what will be the intersection of this? The intersection of this means the final ROC is this, that is modulus of Z is greater than 2. Okay, now this is another example of time shifting. Now here you can see we are having u to the power un of 2 here, but this is a, and a to the power n of 2 is not there. Therefore, this we can split like this: 1 by 2 to the power minus 1, 1 by 2 to the power n minus 2. This minus 3 we can write minus 2 minus 1. Okay, then u of n minus 2. Now we can apply formula to this. So this, the Z transform of this is what? Z to the power minus 2 divided by 1 minus 1 by 2 Z inverse. Okay, and this factor we will solve here. So 1 by 2 inverse is nothing but 2, correct? So the answer for this is 2 into Z to the power minus 2, 1 minus 1 by 2 into Z inverse. Okay, then what will be the ROC for this? The ROC is modulus of Z is greater than 1 by 2. Because this is right sided signal, so will be the ROC will be greater than 2. The outer region, exterior ROC. Okay. Now scaling in Z domain. So if there is a scaling in Z domain, then we will be having this factor multiplied in the H domain. Okay. And what will be this ROC for this? This is very important. ROC will be scaled ROC. Okay. So the ROC will be scaled by modulus of A. Now look at the example given here. Suppose if h of n is equal to the unit step function, unit step signal u of n, find h2 of z where the h2 of n is equal to 2 to the power n h of n. Okay. Now here we can apply the scaling property and we can get the answer. So for the unit step function, we know what is the h of z. So h of z for this u of n is what? 1 divided by 1 minus z inverse. So if we multiply this by 2 to the power n, this is scaled by 2, that is z by 2. Therefore, h2 of z is nothing but this is equal to 2 to the power n h of n z transform of 2 to the power n h of n, which is the scaled z, that is z by 2. So we can write instead of z here z by 2. Okay, so in the scaling property, what you need to write here, instead of z, z by 2 you need to write. So if we solve this, this is basically inverse means 2 by um, if we take 1 by 2 inverse and z inverse separate, so 1 by 2 inverse is nothing but 2, and this is z inverse. Now what will be the ROC for this? So the ROC for this is, what will the ROC for this? So ROC for this version is modulus of z is greater than 1. Okay, so the ROC will be scaled by 2. So the ROC will be modulus of 2, because this factor, scaling factor is 2, modulus of 2 into ROC of u of n. Okay, so the final ROC you will get modulus of z greater than 2. Okay, so this you need to mention, do not write directly here. The ROC is like this. You need to mention ROC will be the scaled factor. Okay, and then you write. Okay, now the scaling in the Z domain. So this example, h of n is 2 to the power n delta n and delta n minus 1, delta n minus 2, addition of this. Okay, now 2 to the power n is multiplied to all this. Okay, so we can directly solve this example, or we can, there are two methods to solve this. Okay, one is the time shifting property we can apply. So if we apply the time shifting property here, so 2 to the power n is multiplied to all here. Okay, now here we can directly write 2 to the power n delta of n is nothing but, just a second. Huh? Now, can you do this example with the time shifting property and the scaling property? Okay, please do this example. I will come in 5 minutes. So are you getting the same answer with these two methods, with the time shifting and the scaling method? Yes, students? Now here, please look at this. Here adjustment is done. 2 to the power n minus 1 we need for this. This is delta n minus 1. Therefore, 2 into 2 to the power n minus 1, this adjustment we can do here. Similarly, this is the adjustment like 2 to the power n, 2 to the power 2 into 2 to the power n minus 2. Therefore, this 4 factor A comes here. Okay, 4 and 2. And then you can apply this time shifting property. Okay, so this is the answer. This is 1 plus 2 z to the power minus 1 plus 4 z to the power minus 2. Okay, the second method here we can apply is the scaling in z domain. So the property, scaling property we can directly apply. So first we will do the z transform for the signal. This is h1 of n. Suppose I say this is h1 of n. So first I will calculate the z transform for this h1 of n. So if you calculate this is 1 plus this z square, 1 plus z inverse plus z to the power minus 2. Now we can apply the scaling to this factor. Okay. So scaling, if because 2 to the power n is multiplied to all this. So if we do the scaling, so this is z by 2. So instead of z, you need to write z by 2 there. Okay, so you will get the same answer with both the method. This is one, this and this answer is same. So you can apply any one method. Okay, now differentiation is if n is multiplied in the time domain, then the z transform is minus z d dz of h of z. Okay, so for example, if we are having h of n equal to n into u of n, so we know that the z transform for u of n is nothing but 1 by 1 minus z inverse. Okay, so if n is multiplied to this, then this is minus z d dz of this. Okay, and this is basically, if we solve this, this is z divided by z minus 1. And we will apply u by v rule here for differentiation and we'll get this answer. Okay, you can try this example at home. And again, in the inverse form, we can write this. Okay, if we divide the numerator and denominator by z square, then you will get this final form. Okay, so in the z inverse form, you can write. Okay, so then the next property is conjugate. So conjugate is like if we are having the complex number like a plus gb, so its conjugate is a minus gb. Okay, so the only sign is changing, that is the imaginary value sign is changed here in the conjugate. Okay, so if we are having the complex number in the polar form like r e to the power j theta, so here r is nothing but, if you write this in the polar form, so the r is nothing but the magnitude, which is under root of a square plus b square, and theta is tan inverse of imaginary part divided by the real part. Okay, so the conjugate for these is nothing but r e to the power minus j theta. This is the conjugate for this polar form. Now, if h of n is given like e to the power j n u of n, then its z transform is this. So if we apply the scaling, then we can directly calculate the z transform like this: 1 divided by 1 minus e to the power j z inverse. Okay. Now find the conjugate of this h of n. So h of n conjugate we can find out like this. The z transform for this conjugate is nothing but it's h conjugate z conjugate. Okay. So this if you apply here, so you will get the answer like this. Now here we know that r e to the power j theta, its conjugate is r e to the power minus j theta. Okay, so here what we will do is minus j e to the power minus j z inverse. Okay, so the answer will be 1 minus e to the power minus j z inverse. Okay, the next property is time reversal. So time reversal is basically the say h of minus n, its z transform is h of z inverse. Okay, or h of 1 by z. And the ROC will also be the inverse of whatever ROC we are having for h of z. So suppose I am having x of n, which is equal to a to the power n u of n, and find y of z if y of n is x of minus n. Okay, the question, please understand, x of n is given. Find y of z if y of n is x of minus n. So here you should understand that the time reversal property will be used. Okay. Now we know that a to the power n u of n, the z transform is 1 by 1 minus a z inverse. Okay. And the region of convergence is modulus of z is greater than a here. Okay. Now to calculate y of z, this is basically h of 1 by z using time reversal. So instead of z, write 1 by z. Okay. Now a factor here, a factor is missed out. Okay. So instead of z here, write 1 by z. So this is 1 divided by 1 minus a into 1 by z. Okay. So a is missing here. You can write here. So this is 1 by 1 minus az. Okay. And the region of convergence for this is inverse of the region of convergence of a. So this is modulus of z is greater than 1 by a. Okay, so this will be the region of convergence for this. Okay, then the convolution property. So convolution basically in the z domain, it is the multiplication. Okay, so if x of n is equal to u of n, find y of z if y of n is x of n convolved with x of minus n. So we know that the z transform for x of n is, which is equal to u of n. This is nothing but 1 divided by 1 minus z inverse. For x of minus n, the z transform is 1 divided by 1 minus z. Instead of z, you need to write 1 by z there. Okay, so 1 by z inverse is z. So y of z is nothing but multiplication in the z domain. So therefore, if we multiply this 2, we'll get this answer. So this is the answer for this convolution. Now, this is another example of convolution. Now, the signal is given in this figure, x1n and x2n. So, how to write x1n? X1n is nothing but we can write in terms of delta. So, this x1n is delta of n plus delta n minus 1. Okay, because it exists at n equal to 1. Okay, so this is x1 of n. The signal x2 of n, similarly, we can represent in terms of delta. So this is delta n plus 2 plus twice delta n plus delta n minus 1. Okay. Now we can apply the Z transform for this. So we know that the Z transform for the x1 is 1 plus Z inverse. For the second signal, the Z transform will be like this. Okay. To find y of Z, which is x1 convolution with x2, so this is basically the multiplication of x1z and x2z. So if you multiply this, so if you solve this multiplication, you will get this final answer. Okay. So like this, we can solve the convolution problem. Then there is a theorem called initial value theorem and the final value theorem. Okay. Now in the initial value theorem, so for the causal signal h of n equal to 0 for n less than 0, that is the causal signal, its initial value can be estimated. So we can calculate h of 0 by doing this limit z tends to infinity h of z. Okay, you can also do the proof of this, but you can see here the initial value theorem says that we can calculate the initial value of h of n, that is at n equal to 0, which is equal to limit z tends to infinity h of z. Okay, now suppose we are having example like this, h of n is given, which is equal to u of n, and find the initial value h of 0. Okay, so we can apply this formula, limit z tends to infinity h of z. So now I know what is the z transform of u of n. So z transform of u of n is nothing but h of z. I can say this is 1 divided by 1 minus z inverse. Now if I put limit z tends to infinity, this 1 minus 1 by z inverse. So this is, if you put the limit z equal to infinity here, so this is 1 by 1. So the initial value h of 0 will be equal to 1. Okay, so this is the initial value theorem. So h of n will be given, so it can be anything. So you need to first find h of z and then put the limit z tends to infinity, and then you can find the initial value. Okay. So for example, um, suppose h of n is given like cos of this function, cos n u of n, find h of 0. So first we should know what is the z transform of cos of n. So this is the z transform for cos of n. Okay. Now let us take n equal to 1 here. Okay. Cos 1 will be there. Then if we apply this limit, so put the value z equal to infinity here in h of z. So you will get the initial value equal to 1 if you solve this. Okay. So like this, we are having initial value theorem. Okay. So all these are the properties of this Z transform. So by looking at the example, you should know which property you will use. Okay. And while solving the example in exam, this is very important topic for the your end sem examination. Okay. Z transform, inverse Z transform, the properties in the Z transform, all these are very important topics. So whenever you solve this example where properties are used, so you should also mention the property. which property you are using, okay, while solving the example. Okay, so I will share the PPT with you, and I will mention some homework example also there in the at the end of the PPT. Okay, so please try these examples and do practice. Okay. So for today, we will stop here. Yes, do you have any doubt? Yes, student.
For now, no, doctor.
Okay, then today we will stop here. Okay.
Okay, doctor.
Okay. Thank you, students. Bye.
Thank
Have
you,
a good day.
doctor.
Thank you, doctor.